This is our second lecture on approximate methods. In the first lecture, we outlined what the two primary methods are for dealing with cases where we can't solve the Schrodinger equation exactly. And that's really the motivation for learning about approximate methods. We learned about both the variational theorem and about perturbation theory. In this lecture, we're going to focus specifically on so-called variational methods. The learning objectives of this video are threefold. First, we want to relate the variational theorem with the so-called variational method. We want to be able to use the variational method in quantum mechanical problems. And then lastly, we want to be able to define and use variational parameters. To demonstrate the variational theorem, at the end of the last video, we showed the wave function shown on the top right here, phi of x. Phi of x is taken as an approximate wave function for the ground state harmonic oscillator problem. This is a problem we've solved analytically already. And so it gives us a nice means for studying the behavior of approximate wave functions as they relate to the variational method and the variational theorem. So we went ahead in the last class and we calculated the energy expectation value for phi, and we saw that it depended on beta, this variational parameter. And I mentioned in class that the wave function phi of x with this parameter beta is really a family of wave functions. And beta gives us a means to sort of change between members of a set of types of functions. And that if we do that, we can write the energy expectation value again as beta, and we can plot that. And we see here the yellow curve, which is the approximate wave function's energy expectation value, and the blue line that just shows us where the exact ground state harmonic oscillator energy is. And at the end of the last video, what we ended up saying was that this was proof, or at least a demonstration, of the variational theorem, that all values of beta, which correspond to different members of the family of functions phi, all have energy expectation values that are greater than or equal to, and in this case only greater than, the exact wave function's energy. And we ended that video by basically saying that, one of the nice things we could do now is to think about finding which member of this family of wave functions is the best approximate wave function. That gives rise to this idea of the variational method. What we're going to do is we're going to treat beta as a knob that we can turn to tune ourselves to the best wave function in this family that we're studying. And then we have to define what we mean by best. And what we usually mean is the wave function whose energy expectation value is closest to the exact energy. And so what we'll try to do is to find the value of beta that points us to the minimum, which I'm showing here with the arrow. We do that by, again, writing down the expectation value and then taking its derivative with respect to beta and setting that equal to 0. At 0, the curve that we're studying, in this case the expectation value for the energy of phi, is at a minimum or a maximum. And in this case, we'll only worry about the minimum case. So we set this equation to 0, and we solve for beta. And we see that beta is equal to the root of 2 mu k on h bar. We can plug that value of beta back into phi, which I show at the bottom of the slide now. And we put everything together, we'll see that the best value for the energy expectation value one of the members of the family of functions phi can give us is given here at the bottom. The term in parenthesis I've factored out because that's actually the energy of the ground state harmonic oscillator. H bar on 2 times the square root of k on mu. And you'll see that the energy expectation value for phi with the most optimal choice for beta is the square root of 2 times that value. It's greater than the value of the exact wave function as we expected, but this is still not too awful. It's not that great either. The error here is about 40% in terms of energy. But the idea of the variational method is exactly this. We look for the value of some parameter that we're allowed to change or tune in our family of functions, and we look for where the optimal value is, and when we say optimal, we mean the value that leads us to the lowest energy expectation value. Again, You just take the derivative, set it equal to 0, and solve for the parameter. There is an alternate form of the variational method, and in fact it's probably the most widely used form of the variational method in practice. And it's often referred to or called the linear variational method. The idea is this, that another kind of wave function that we can use to approximate the exact wave function could be given by some linear combination of two or more functions. So what I show on the left here is that some approximate function phi might be given by some coefficient c1 times some function that we know little phi of 1, and add that to c2 times phi2 and so on and so forth, which I can write in the more general summation notation below. Now in this case, all of the c's are our unknown variational parameters. We can change the c's and get different admixtures of the different functions we've included, and we'll get different energy expectation values. And if we choose the values for the c's that give us the lowest energy, then we can approximate or assume that that form of our function is the most optimal or best representation or best approximate form of the exact solution. One thing to say about this is that if we were to plug in big phi into the energy expectation function, as I've done here, and I'm assuming in this expression that big phi is normalized, so the denominator from the expectation value expression that we know is not shown. But you'll see that because the Hamiltonian is linear, I can factor out different terms, and I ultimately end up with something that looks like a product of C1 star and C2 times integrals or bra-ket combinations that have one of my functions in the bra, one of the functions in the ket, and the Hamiltonian in between. And the one thing I should say, because I'm kind of going through this briefly just to give you a flavor for what the linear variational method looks like, is that you can see that from the middle set of equations, there'll be a whole bunch of terms that come about by doing all combinations of terms on the left and terms on the right. This is basically just using FOIL if we only had two terms, or more of that kind of factoring process. And what I show in the very bottom equation is just plucking out one of the terms, in this case C1 phi1, Hamiltonian C2 phi2. And what you'll see is as I go through all the different integrals above, I get these elements that look like one of my functions phi I with the Hamiltonian next, and then the ket has phi j, whatever that is, some other phi. And I get all combinations of my various functions with the Hamiltonian. And since there's always one in the bra and one in the ket, I have a series of what look like matrix elements. And so you'll see in the last expression here, I've written one term from the middle set of equations simply as C1 star, C2, H12. If I took the first term that was expanded above, I'd have C1 star times C1 times H11. And if I took the second term, I'd have C2 star times C2 times H22. As a result, when we have a function in a bra, an operator, and then a ket with another function, we often refer to those integrals as matrix elements, especially within the context of the linear variational method. Now, the key thing to take away from this, and your book talks about this a bit, is that once we get to matrices and we have a whole bunch of C's to solve, it turns out that this looks like a very conveniently structured linear algebraic system of equations to solve. We basically have matrices and vectors, and we have to solve for the best choice of the C's using some derivatives, and ultimately using this kind of linear algebra approach is exceptionally convenient on computers. It's harder to do by hand, but as I said, this is probably one of the more widely used, possibly even the wideliest used version of the variational method in quantum chemistry, especially because we can code it up on computers conveniently. So quickly to summarize, the variational theorem gives rise to this approach that we refer to as the variational method. Variational parameters can be used to find a best approximate wave function from some family of approximate wave functions. And there is a particular form of the variational method that, as I point out, is exceptionally convenient on computers, called the linear variational method. that's it for now. In the next video, we'll turn to perturbation theory. I hope everybody's doing well, staying safe, and staying healthy, and I'll talk to you soon.